In this lesson, we're going to talk about geometric distributions. In a geometric distribution, you find the probability of an event occurring after it does not occur a number of times. So much like binomial distributions, trials in a geometric distribution have only two possible outcomes, success or failure. These probabilities do not change from one trial to the next, so of course they're independent. However, the random variable for a geometric distribution is the waiting time, the number of unsuccessful independent trials before success occurs. And if you can't read my messy little side note here, the waiting time is the key characteristic that distinguishes a geometric distribution from a binomial distribution. So, like I just said, in a geometric distribution, you find the probability of an event occurring after it does not occur a number of times. So, some examples in a board game, you sometimes like Monopoly. You can't get out of jail unless you roll doubles. So, there's a certain amount of waiting time that's involved. Manufacturers of products such as hard drives need to know how many operations their products can perform before failing. In some sports competitions, the winner is the player who scores the most points before missing a shot. So these are all examples of situations where there's a waiting time. Okay, the formula for probability in a geometric distribution is P of x is equal to Q to the power of x times P, where P of x is the probability of the event first occurring after x is the independent trials, and P is the probability of success, and Q is the probability of failure. So now let's talk about the expected value. So the expected value is equal to an infinite series of the number of trials times its probability. So the reason why this, if you recall, this symbol right here is called sigma, and it just means added up, right? So we're using it to represent an infinite series here. Our initial point, we're starting our trials from 0, and the reason why it's infinite is because there's a waiting time involved, and so we don't really know when our successful outcome is going to occur. So we're taking the worst case scenario here, so it would be infinity. It's possible to show that this expectation converges to a simple formula. We could show that using calculus, but I'm not going to. I'm just going to skip over that part. Okay, so this series converges to Q over P, so the number of failure over success. Okay, for our example, we want to find the probability of not rolling a 4 with one die until the third roll. Okay, so let's list our variables here. We know that x has to equal 3 because that's what we're evaluating. We want to figure out, so our successful trial is going to be the third roll. And then we know our success is going to be 1 out of 6 because that's our probability of getting rolling a 4. And our failure, therefore, is going to be 5 out of 6. Okay, so now we're just plugging that into the formula. So P of 3 is going to be 5 over 6 to the power of 3 times 1/6. And that comes out to 125 over 216 times 1/6. And that's 125 over 1,296, which comes out to 0.096, and that is 9.6%. So the probability of not rolling a 4 with one die until the third roll is 9.6%, just under 10%. Okay, so the second part of this question asks, how many times would you expect to roll the die before rolling a 4? So we're looking for expected value, and the equation we're going to use here is just Q over P. So we don't need to do the entire distribution, we're just asked for a specific expected value. And our Q we said was 5 over 6 divided by P, which is 1/6. And for those of you who are a little rusty with your algebraic manipulations, I will walk you through this. So you're going to, if you're dividing a fraction, you're just going to take the reciprocal, so you're going to get 6 over 1, and then these cancel out, and you're just left with 5. So what does that mean? That means that you would expect, on average, to roll the die 5 times before rolling a 4. Now let's look at an example where we're dealing with the distribution. So find the probability distribution for the number of shots taken before scoring a goal if the probability of scoring a goal on any given shot is 10%. So we're looking for a distribution, therefore we know we need to make a chart. And let's write down our givens. So we know our success is going to be 10%, so 0.1. Therefore, our failure is going to be 90%, so 0.9. And we also, I'm just going to rewrite our equation for our probability, and that's q to the power of x times p. And of course, our chart is that. Okay, so let's start from 0. And we don't really have a stop time, so this can go on to infinity. I'll probably usually give you, I'll say after 6 trials or something like that, but let's just go till 3 or 4 to get the general idea. So for our first trial, or 0, when x is equal to 0, so this is before we even start. What's our probability? So let's plug our values in. So our q is 0.9 to the power of 0, and anything to the power of 0 is 1, so this is just 1 times 0.1. So that's just equal to 0.1. So your chances before you even start are 10%. That makes sense. That's given in the question. And now this is our first trial. So that's just 0.9 times 0.1, and that's going to give you 0.09. Notice how your probability of success just went down after you took the first shot. Now for the second shot. So 0.9 to the power of 2 times 0.1, and that comes out to 0.081. So even lower. As you can see, this is a decreasing function, and it might have asymptotic behavior. And this comes out to 0.0729. So you can go on to infinity, but let's just stop there. And now let's graph this. Okay, so as you can see with the graph, there's a gradual decline, and it's going to continue. That pattern is going to continue. There's an asymptote at 0, but as you'll notice, the highest, for a geometric distribution, usually the highest probability is going to occur before you even start. Okay, so the second part of this question asks, how many shots would you expect to take before scoring a goal? So we're looking for our expected value, and we're going to use Q over P, and it's just 0.9 over 0.1, which is 9. And so that means that you would expect on average to take 9 shots before scoring your first goal. Here's a little math joke, and thanks for watching.